Okay, again, thanks for joining us today. Before we dive into the presentation, I did want to share a little bit of information with you. We are recording the session. This is a question that we frequently get, but yes, we're recording all the sessions. They will be available. They will be available via our website at monolithicpower.com/webinars. And for all our registrants, we will send out an email notifying you when they're processed. It usually takes us a couple of days to process and edit a little bit, and then we'll post it out and have it available to you. You will notice with your Zoom webinar interface that you are muted when you arrive, and you will stay muted. We will have a question and answer session at the end of each presentation. So if you have questions come up, just mouse over your Zoom webinar interface, and then you'll be able to type in a question under Q&A. We'll read those off at the end and make sure that we address them. Whoop, that's yesterday's agenda. Today, just wanted to let you know, first topic, we have Christian Cook here, who will be sharing with us spread spectrum techniques to help reduce EMI. After that, we'll have Todd Taberski covering two radiated EMI topics. And then we'll wrap up with Mark Malik, who will cover reintroducing a two-layer PCB design. And with that, I will go ahead and turn it over to Christian.
Okay, so stop doing yes. Let's see this one. Share. So good question. Do you see now my blue screen here with spread spectrum? I hope it works.
We do see you, Christian, and it sounds good. So we will just let you proceed from here.
Okay. So I am now 22 years with my former company, Linear Technology, and 6 years as Monolithic Power Systems in an FAE position, mostly dealing with power supplies and EMI and so these issues. So pretty long in the industry on that one. Today we will talk about spread spectrum, the motivation, why we do it. Look how a non-spread spectrum system looks like, and we'll look if what effect the switching frequency duty cycle on EMI had, and then we will dive in what spread spectrum can do for us. And then I talk a little bit about methods to make spread spectrum. You might wonder that most times it's already inside of the power supply controller IC, but you have also a capability, even if it's not come with the IC, to do that. And then I'll go a little bit about typical FAQs which come, and then we go over your Q&A. If you look into the EMI measurements of a typical fixed frequency switcher, often you find that you are a little bit above the limits, so you have to do something, which typically means that you have to shield, filter, change your layout, and so on. There is also another possibility to get these spurs below the limit line is if you just manage to get the energy of the individual spurs down. And one way to do that is to make the spurs wider, and with the same energy, if you make the spurs wider, now they will go down in amplitude, which means now you might pass the limits, and that's what typical spread spectrum tries to achieve. Fixed frequency switcher has a comp-like type of spectrum. So you have a spectrum which consists from the switching frequency and all the harmonics, so 2, 3, 4 times and so on. And if you look on the switch node of a switching regulator, you will see that it's fairly flat now. So you have here spectrum up to 300 megahertz. So it goes a little bit down, but you can assume that in general you generate with a switching regulator a comp type spectrum which goes pretty much wide out to high frequencies, and that's what you have to cope with. If you go higher, you will see at a certain point, as everything in physics, energy is not infinity, which means there is an crossover point here in the range of 400 or 500 megahertz, where actually the energy goes down. Here, these spurs are actually a GSM base station where my shielding wasn't perfect, so forget about this one. But here you can see now that for higher frequencies above 500 megahertz, the energy goes down, and that's some free nice thing physics provide you. First, we want to look at what the typical duty cycle does for the low harmonics, so the low energy spectrum. So we see here from 150 kilohertz up to 10 megahertz, the frequency. Here we see in yellow the duty cycle, and if the switching frequency goes up, I see that here, like in VCO, the red line will be the frequency going down, and it's a video, and with some luck it will play. So we see that if we lower the input voltage, duty cycle goes up. Now we'll see that lowering the input voltage, and it changes actually the spurs, and there's a certain voltage you could see at 50% duty cycle where all the even harmonics disappear, and you see now that the lower end harmonics from their shape change with duty cycle, and duty cycle changes a little bit with load, but especially with the in to the out differential, which means if you make any measurements, now you have to compare them as the same V in to V out differential. And if you go to fairly high input voltage, you get a low duty cycle, but you could see now that you get fairly high spurs, now, which means that your spurs also go up with input voltage. Now, if the input voltage is higher, now you see higher spurs. If we make the same thing now with higher frequencies, now we'll see that's now the switching frequency. If we change that, we will see now that if the switching frequency goes up, now you get more spurs, or less spurs, and the spurs are moving in this direction. And also the spurs with higher switching frequency go up. So you can clearly see that even the individual spurs get more energy as you go up with switching frequency. You have the benefit, you have less spurs, so the distance is always the switching frequency in between. You get less now, but with increasing of the switching frequency, you increase the energy of your individual spurs. Which means now that most times it's not a simple escape path just to raise the switching frequency that you get away with, say, smaller filter components. So in general, EMI energy goes up with switching frequency. And that's also true for the higher frequency range. I make now the same experiment, and here I look from 150 kilohertz to 300 megahertz. So for the start, I think at about 400 kilohertz, I shaped the red shape, and now we see what happens if we increase the switching frequency from 500 kilohertz to 1 megahertz. Now we see that we get a roughly 60 dB increase, and if you go up to 2 megahertz, now we get an 12 dB increase. So in general, we get 6 dB more energy for every doubling of frequency in a fixed frequency environment. I just want to make sure that you have an idea now what the impact of switching frequency in general is on EMI energy. If we want to reduce the say measured energy, we have to look a little bit how the measurement systems, the EMI receivers, actually work. Now, typically it's an superhead mixer, and standard receiver, and get a mixer first interface. And the important filter is actually the receiver bandwidth filter or resolution bandwidth filter. And that is set to a bandwidth and -3 dB bandwidth of 9 kilohertz in the 0 or 150 to 30 megahertz range, and it will be set to 120 kilohertz above 30 megahertz and below 1 gigahertz. So it has a certain shape which is similar to, say, the IF filters of the older radios, because that's what's EMI all about, to look for not to interfere with radios. But that's for the look what an EMI receiver and Spectral can do for us. The most important filter, it's actually the resolution bandwidth or receiver bandwidth filter here. You have in an EMI receiver and spectrum analyzer also filters after the rectifier, now, which makes essentially the power, and you get then low frequency filters which measure quasi peak, or average. However, they have in a sense not as a big impact as the resolution bandwidth or receiver bandwidth filter. So that's the important one, and we'll later come to it now why is that the case. In general, if we know that we do a comp-like spectrum, how can we get rid of, say, our energy, or how can we disperse energy? So what we can do is we can move these Spur around right and left, and in a sense, what your receiver does, so your receiver bandwidth filter, you can assume that your EMI receiver just moves its receiving filter through these spurs. So what you measure will be the spur widened up by the receiver bandwidth filter. So you get actually a convolution operation. So you move the filter through these now you get a real convolution. So what it looks like at the end is that every spur is widened up by the receiver bandwidth or resolution bandwidth filter. And if you think what you can do to reduce the energy, I mean, you can try to get the spur energy in the area in between. So here are the dead areas where your EMI receiver does not see any energy. And so what you can do, if you could distribute that absolute evenly, you could reduce your peaks to a white noise spectrum, which just looks like the what's the energy of these blue lines shown. So that would be the perfect spread spectrum. You can't get there, but you can try to get close. But if since we know now the area of these area and also the area in between, we can immediately say, okay, what is the maximum attenuation a perfect white noise style spread spectrum can provide us? Now, and for the 9 kilohertz resolution bandwidth or receiver bandwidth, you can immediately see at 400 kilohertz switching frequency, the maximum attenuation a perfect spread spectrum could provide would be 60.5 dB. And if the receiver or resolution bandwidth is wider, you get less area, free area. So at 120 kilohertz receiver bandwidth, you only get 5.2 dB. So clearly see now that as wider the resolution bandwidth is, as less potential attenuation you get. And especially above 1 gigahertz with 1 megahertz wide receiver bandwidth is very difficult to get any attenuation at all. So the highest attenuation you get in the lower area in the 9 kilohertz receiver bandwidth setting up to 30 megahertz, and that's typically where the most problems occur. And since you get the best return on your investment in EMI, typically it's best not to optimize in that area. So we know that a filter has a step response, which means as long as the spur is within that filter range, it will go up to full blast. If I am only a short time within these filter area, I have to make sure that I have to be less than the settling time of the filter bandwidth of a low pass with the same filter bandwidth in that area to get any attenuation at all, which means that if I in a 9 kilohertz resolution bandwidth filter, if I'm fiddle around more than 111 microsecond within that area, I don't get any attenuation at all. So I have to move faster than 1/9 kilohertz through that range to that my EMI receiver get any attenuation. It's 120 kilohertz is worse, which means that in this wider area, I have to spend way less than 8.33 microsecond that I get any attenuation. Otherwise, my EMI receiver will show full blast. So that's, I think, the second limitation. We have to move the frequency around fast and outside of these receiver bandwidth filters. And that has an impact on the type of modulation and the shape of modulation signals we can use. So in general, we can say now that for 9 kilohertz receiver bandwidth, our carrier have to move faster than 81 megahertz per second. And at 120 kilohertz, it has to move faster than 14.4 gigahertz per second. So that's actually change of frequency here. Okay, if we want to do something on a switching regulator, we want to have constant output power, constant output voltage, which means we have to use a modulation which does not create amplitude modulation. Amplitude modulation would directly give output voltage variation. We want to avoid that. So we are forced to use a frequency modulation or phase modulation. And any phase modulation we can look is determined by its modulation frequency, the modulation depth, which means how much I change the Spur, the main carrier, and the quotient of that will be the modulation index, which means that the modulation depth divided by my modulation frequency will get my modulation index. And if you want to get an idea how much attenuation frequency modulation can give us for these spurs, it goes down with modulation index. So high modulation index would get us a lot of attenuation. So from first glance, would means the best would be to get a modulation signal which gives a high modulation index. If we have, say, a delta F of 20% or so, which means now that low modulation frequencies would give good attenuation, because that would give high modulation index. But the problem with it is that on the other side, low modulation frequencies will give slow moving carriers. So they violate the time domain view of the 111 microsecond or 8.33 microseconds. So in reality, these thing will go up here again. And I will give you an example here. With low modulation index at high modulation frequency, so we start at 122 kilohertz. So here you see the modulation signal. Here you see the spurs. So you see nice two spurs, 122 kilohertz apart. And if we reduce the modulation frequency, we see now that the spurs go up. We get more and more spurs. And actually the main also goes down. But we are still relatively high. And that actually is the gain we get now, the attenuation or spread spectrum signal will give us. And we immediately see that around 9 kilohertz or so, we get the optimum. We get a good 10 dB attenuation here. And that's all very close around the carrier of the baseband. So I use here a triangle modulation signal in the time domain. And if I go back up, you can see that the spurs go out. So that's what you really expect from normal FM modulation theory. Okay, over a wider frequency range, not just the carrier. Now we look at the same situation. We start with high modulation frequency and move the modulation span up to 20 kilohertz, and we immediately see now that we get now this attenuation here in the higher area. The low area we get a little attenuation, and only if we move the modulation frequency down, now we get also in the lower frequency area a decent attenuation. Now you can see now that the spurs get get wider and wider now, because that's linearly frequency here. Now, so at a certain point you get to the overlap region. If you are within the overlap region, typically you do not get more attenuation if you change the modulation frequency. And here you can see now what happens if you go very low with the modulation frequency. You can see that especially at the lower end, the spurs go up again, so we get less attenuation. So that's around 8 kilohertz, which means that if you want to optimize for the 30 megahertz area with 9 kilohertz resolution bandwidth, also modulation frequency, which is in the 9 kilohertz area, will create best results. So it's not really necessary that you're absolutely at 9 kilohertz, could be 8 or 10 or 11 or something, but around that ballpark, that usually will work best. And now if we change the modulation span, let's see, modulation frequency, and now if we change the modulation span, so here we keep the modulation frequency at 9.2 kilohertz and move the span around. Now here we with that little span, we don't even get overlap. Now we also see that too little span will not give optimum results. And if we increase the span to whatever 10-20% or so, now we get here into the overlap region and we get here optimum results. Most time it's not really necessary to go extremely high with span. Now it doesn't do much here in the overlap region, and in the base area you get a little bit more. Here in the red now you see directly the triangular modulation signal I'm using here. So you can see very high modulation spans do not give you much improvement. Okay. Now the same situation, but for the 120 kilohertz resolution band area. Now that's usually for the higher frequency above 30 megahertz. Now, so I have here the CE range from 30 megahertz up to 100 megahertz, 108 megahertz. Now let's see what happens. Now I move the modulation span up to whatever 20%. Now we immediately see we get about 5 dB attenuation, and now we can play with the modulation frequency, and we'll see if we go very low with modulation frequency, we would lose actually attenuation. Now, so for the high frequency area, high receiver bandwidth, high modulation frequency would work best. Now you can see now that you can see the high spurs. So if you would make really peak hold, you wouldn't get much attenuation or spread spectrum here. So for the 100 kilohertz setting, high modulation frequency would work best. So also optimum would be in the range of 100-120 kilohertz, but it's probably unrealistic not to go that high with a modulation frequency. Okay, so what we learned is now that for the attenuation, there is an optimum frequency typically around where the receiver bandwidth lays. Now for the lower than 30 megahertz range, modulation frequency around 9 kilohertz would give optimum results. For the 100 kilohertz receiver bandwidth area, for the higher frequency range, it would be 120 kilohertz. Now, so it means we should not and cannot go too low with our modulation frequency. We also cannot go too high to get decent results. There's also an implication of the type of modulation signal we can use. No? So high frequency gets low modulation index, low modulation frequency gives low resolution bandwidth filter impulse response situation. So if we look on a modulation signal, we learned now that we should keep moving. Now we should keep it at 81 megahertz per second or so. And the problem is our modulation signal needs to be periodic now, because we cannot go to infinity with that. Now we have to, at a certain point, get back to the start point, and there are several ways to do that. And if we use a simple modulation signal like a triangular, here we are fine, so we have a constant change, but the problem is that in the turnaround point now we spend actually double the time in that frequency, or we at the same time we only move through half the frequency because we're moving backwards. So always the area where we go backwards in frequency is the problem area. And there we would less attenuation. Now, there's one thing we could cope with. We could use a Sawtooth. There's nothing wrong from a spectral side to use a Sawtooth. The only problem is that at this point we change the modulation frequency or the switching frequency immediately. And depending on your switcher control loop topology, you might get in trouble if you do that. Now you get an additional output ripple. Now, so in theory, you could do that, but in practice, now that a lot of cases that creates some trouble, it creates more output ripple than necessary. Now, so what you could do is you could sharpen up the edges. Now, so it calls Hershey kiss, I think from American chocolate here, a type of signal. The other would be that you just make a step here. The idea is that you spend equal times in equal frequency changes. So that's a modified. They will go both get same results on modulation on spread spectrum effectiveness. If you have an internal generator for spread spectrum, normally you have no choice to fill around with that. You have to take what the manufacturer gets you. If you have a power supply controller which does not have inherent spread spectrum, it's not the end of the world. Very often you can set the frequency with an external frequency setting resistor, for example, or MPQ 4430, and there's lots of series we have. We just set the switching frequency with an external resistor, which usually means that there's an internal current source and it measures the voltage here, and depending on the voltage, sets the VCO, the switching frequency, which means that we have a handle where we can actually change the switching frequency. And so with a little bit of modulation signal injected here, and I've taken these 169 kilo ohm resistor and taken in 168 and bottom 1K and a low pass filter. So you can just feed in here over an capacitive coupling, a rectangular signal, which makes a nice triangular signal with roughly 100 millivolt peak, and that will create a nice spread spectrum signal. So here you see the effect of spread spectrum this small circuit creates. And in a lot of cases, your square wave generator, you have it on a microprocessor free if you have a port pin or timer output or whatever, or if any say 9 kilohertz-ish generator, then you can make a simple, very low cost spread spectrum machine, and that's successful, used by some of our automotive customers, for example. Also, we have parts where you can set the spread spectrum and can check it digitally with modulation range. the modulation frequency, you know, can set it off and on. And I mean, I could run that now, but it will give the same results as we have seen. In general, it makes no difference if you create your modulation signal in an analog way or in a digital way, no? Because you only are interested on the next start of the PWM cycle. In general, spread spectrum works independently from any other EMI mitigation things like layout and so on. So that's always added attenuation, which you get over other method. Problem of spread spectrum is it naturally gives you some frequency and with that some duty cycle jitter. So I recommend, if you troubleshoot a power supply, set it to fixed frequency, make your necessary measurements about step loads and these things, and look that the switching frequency and duty cycle is nice and stable. And if that's all done now, then change it to spread spectrum. Because spread spectrum can hide in initial instabilities of your loop. No? So it's always good now if there's a means not to switch off the spread spectrum. In general, spread spectrum adds minimal additional output ripple to fixed frequency designs. On non-fixed frequency loop topologies like constant off time, constant on time, hysteretic, and any other fixed ripple designs, most times you don't see anything at all. So typically, spread spectrum does not change your step response, does not change your loop stability and these things. What have we learned? Now, EMI goes general up with voltage on the switch node. No? So it goes up with 6 dB for every doubling the switch node voltage. And it also goes up with switching frequency. No? So it goes 6 dB on a fixed frequency switcher for every frequency doubling. And on perfect spread spectrum could buy you 3 dB back offset. No? So even on spread spectrum switcher, if you double the switching frequency, you would even on the best white noise spread spectrum still get a 3 dB increase per doubling of the frequency. Now, so in general means that for low voltage designs, 3.3 volt V-in PMIC types, run them at 2 megahertz or above, because in general your voltage is not that high, your inductors are not that large, so that gives you best step response and best overall results, and without violating or bunch EMI problems. However, if you have high voltages like 12 volt car battery 2448, then you move around high voltages and you get a lot of EMI trouble. And for these high voltages, most times keeps the switching frequency as low as practical. Now that would mean automotive sub AM band. If you have an internal oscillator, the oscillator is not a crystal stable, it has some phase noise, some FM. And the FM goes up by the harmonics, which means that something which looks pretty nice at 1 megahertz will have a decent phase noise at 100 megahertz and above. So a normal switching regulator gives you some natural spread spectrum, some natural phase noise. If you force now this switching regulator with an external high quality, high Q crystal, it very easily can be that something which passes EMI with the internal, say, noisy oscillator, and since you have it really set close with a high quality oscillator, then all of a sudden you violate your EMI goals. No? So don't wonder that if stiff synchronization makes your matters worse. Okay, so what have you learned? Spread spectrum is an excellent tool to reduce EMI with little additional cost. Optimum modulation frequency is always at the receiver/resolution bandwidth, around the resolution bandwidth. Optimized for the 9 kilohertz area, there you get the most bang for the buck. And also on the low frequency end, it saves you the most with the reduced filter and shielding requirements. test the power supply with a fixed frequency setting. Even if you don't get an if your part is spread spectrum, you can't do that. Very often we have pin compatible parts which are fixed frequency, and you can test with them. Parts with an external frequency setting resistor can easily be made spread spectrum, as long as you have some rectangular signal around now, which is in the whatever 9 kilohertz or something area frequency. On excessive frequency span only helps for the lower harmonics, but not in the overlap region. For the 100 kilohertz, 20 kilohertz region, it's very limited what you can, what spread spectrum can do for you, because you have less effectiveness. Okay, I have some Q&As to go through now. So typical question now, how many dB spectrum can you get from spread spectrum? Now, so at 9 kilohertz resolution bandwidth, now at 400 kilohertz, 60.5, at 2 megahertz, 23, the 120 kilohertz region, even less. Does spread spectrum affect transient response? It has almost no effect of it. So it's another one. Which algorithm is used to generate spectrum inside MPS DC-DC converters? We have two methods. One is a small analog triangle signalator or step triangle generators, and there's also a digital implementation used. But they are both have the same effect, so it shouldn't bother you what internally we do. What's a frequency modulation shape or envelope is most effective? Sawtooth, triangle, or sinusoid? Can also answer that. No? So sawtooth would be most effective. Triangle a little bit less. No? The Hershey kiss would be best. Sinusoid would be worse because you tend in the turnaround region, you stick for a very long time with small frequency changes. No sinusoid, so it's not a good modulation scheme. Yeah, what cost difference is anyway is to expect it from a spread spectrum part to a non-spectrum part. Sure, the spread spectrum part needs an additional modulator to change the frequency, but that's typically compared to the main power switches not a big deal. And also we are talking a few percent of die area. Now, so it's very little additional cost what we would have. Does spread spectrum really help on EMI, or is it just a cheat on test equipment? I mean, the energy you create and you emit to the universe will be the same. However, the test equipment, our EMI receiver, which tells us if we pass or fail, will get different results. So you can answer that yourself. In which area spread spectrum does help? Conducted emission, radiate emission, only lower 30 megahertz or greater, it helps everywhere. Is there any secret military or patented spread spectrum method that gets more attenuation? Simply since we have raw physics here, no, as the formula I've chosen, no, so there's no escape to physics. It's actually the we can derive that to deep quantum physics, to the Heisenberg equation, what you can get from spread spectrum. Is random or phase noise random modulation, is it a bad choice? And we have learned that low frequencies and high frequencies are bad. If you do pseudo random modulation, most times you cannot avoid that you are for a longer time in the lower or high frequency area, which means is very difficult with pseudo random to get optimum EMI results. I mean, you can shape your pseudo random that it sticks around the optimum frequency area, but on a scope, it would then pretty much look like a triangular modulation. So that's you do not get much additional for it. We at MPS provide you with a lot of support on EMI. So here we have an EMI lab in Ettenheim in operation with 3 EMI chambers. We have an SIC 6-meter chamber. We have an automotive system 25 chamber. We have also in Detroit, USA, where these seminar is hosted, full blast, similar EMI lab, and we have also an EMI lab in Hangzhou, and we are happy to support you there with these problems. I think that should finish my presentation here. Thank you.
Great, thanks, Christian. We did have some additional questions for you today, though. So the first one, I think you had an FAQ that sort of addressed this, but kind of a statement here. Spread spectrum strategies have always struck me as a sort of trick that is aimed at complying with an arbitrary set of rules, passing whatever standard is being tested against, as opposed to considering whether the aggressor DUT is truly less offensive to victim devices. Could the presenter address whether the emitted EMI is actually more benign in terms of not causing ill effects in other devices? Intuitively, it seems like more energy is actually being emitted if we look at area under the frequency domain curves.
Yeah, I mean, the thing is, the energy you create and emit to the universe is the same on fixed frequency or spread spectrum. Just the spectral distribution is different. And it's a question how sensitive your system is to these spectral distribution. If you, for example, have a high resolution A2D system, then sometimes it's necessary to absolutely synchronize your A2D converter with some critical switching frequencies. So at these points, you cannot use spread spectrum techniques. But in most cases, you can use spread spectrum because the noise your other system, special processes, are also sort of random or pseudo-random. So, I mean, at the end of the day, your boss asks you to pass the EMI test, and that's about it. And the other is, say, a philosophical question. However, typical engineers are paid for solving specs and solving problems. So if it passes, it passes.
All right. And then the next one up was, do multi-phase controllers like the MP2940 support spread spectrum?
I think yes, because normally if you have a master oscillator and that's divided for the different phases, there's nothing wrong with changing master oscillator's frequencies. Even if you have, and say, not a divider, but a time delay from one to the other, you could start with your master with the spread spectrum, and your slave would also be forced to run in spread spectrum. So in general, there's nothing wrong with running multi-phase systems with spread spectrum.
Now we have, how do you avoid the audible noise being generated when using the spread spectrum?
Normally FM means I have constant output energy. So I can only hear audible noise if I really have power changes, and which means I have some sort of AM content. So typically, if I do not use parts which are by their nature low frequency speakers, spread spectrum shouldn't result in audible noise. AAM mode is a complete different story, because that's, say, 100% AM and creates a lot of, say, audible noise, or can create an audible noise in an MLCC output capacitor. But spread spectrum should not, if it's done correctly.
Great, thank you. Next up, can spread spectrum become synchronized, which is not intended unwanted in a system?
You can, if you start with a master spread spectrum oscillator, synchronize a lot of other stuff to it. So if the other systems can cope with that, say, modulation scheme and can be moved around, no problem. Why not? I mean, it's normally always done if you, say, do spread spectrum on a processor clock.
And next up, I have a question pertaining to some of yesterday's discussions. Okay, yeah, if you have questions from yesterday, you can go ahead and just email those to me, and that's kelly.curd@monolithicpower.com. KELLY.CURD at monolithicpower.com, and I'll make sure that we address those. Next one, are these MPS Labs automotive OEM recognized or ISO 17025 accredited, or is it just more for pre-compliance?
No, we are planning on accreditation. Also, we are working on that, and we are complying with the automotive standards. But up to now, to my knowledge, no, they are not accredited by any OEM. But I do not see that as an, say, big problem up front, because they are all implemented with most modern, up-to-date equipment. So there's no reason that they should be any not giving you a true up-to-date results.
Great. And then I think we have over in the chat window, we had, so I think this was back to one of your videos, the modulation frequency video. Was the waveform demo done in simulation or actual bench test?
No, that's actual bench testing. I mean, we could see really a spectrum analyzer, which is in Rohde and Schwarz FSL3, no? And you could really see the generated oscilloscope. No? So I used an Ozong 2-channel oscilloscope. No? So it was all real-time measurement. There's no simulation I used at all in the whole presentation.
Great. And then the second part to that was, if simulation, what tool was used? I don't know if you have any simulation tools that you could recommend, Christian?
Yeah, I mean, I did write my own with, I mean, if you go into FM modulation, I mean, it's a fairly complicated. No? So the nice thing is that Excel can give you a lot of help on that now, but expect now that for a simple model simulation, it takes several minutes now to get decent results. And yeah, I mean, the nice thing is practice and theory really match if you take everything into account. So that from a normal modulation theory, you get into what you really get on attenuation, but you have to also look not only the frequency domain, what typically the modulation theory does, you have also to look into the time domain, which means what is the settling time of your receiver/resolution bandwidth filter.
Great. Thank you very much, Christian. It looks like we've addressed all the questions.